Hello, I am Christian Malaga, and this video will discuss the free vibrations of undamped single degree of freedom systems. The key concepts discussed in this video are the role of the initial conditions on the free vibration of single degree of freedom systems and the definition of the natural circular frequency of a single degree of freedom structure. This figure shows a single degree of freedom system comprising a mass m restrained by a spring of stiffness k and a dashpot with a damping coefficient c. The mass is subjected to a time-varying force F that causes a time-varying displacement U. However, before embarking in the analysis of the dynamic response of a structure to external loads, it is essential to, in colloquial terms, understand how the structure prefers to vibrate, or more precisely, how the structure vibrates in the absence of any external force. Thus, we can consider its free vibration characteristics as a property of the system. Free vibrations can be thought of as a special case of the forced vibration case when the external force is set to zero. Moreover, in this short video, we will concern ourselves only with the simplest case of a mass spring system with no damping. In such a case, the equation of motion is reduced to mass times acceleration plus stiffness times displacement equal to zero. We are going to solve this equation using three different formulations. A first formulation expressed in terms of a cosinusoidal function with a given amplitude A and phase phi. A formulation B based on the sum of a cosine and a sine function. And a formulation C based on complex exponentials. You can appreciate that those correspond to three alternative ways to express a harmonic function. Let's start with formulation A, amplitude and phase. The standard procedure for the solution of the ODE governing the motion of an undamped system without any external force, shown in the right, starts with the postulation of an ansatz. Remember that the ansatz is an educated guess. In this case, we choose a simple cosine function as our ansatz, and we postulate that the motion of the system can be represented by a cosine function evolving in time t with an amplitude a circular frequency omega sub n, and a phase phi. Differentiating our ansatz twice, we arrive to accelerations. In this case, we have that the accelerations will be equal to minus a omega n squared times the cosine of omega nt minus phi. Remember that we are using the dot notation for differentiation with respect to time. By substituting these two expressions for u and u double dot in our original equation of motion, we arrive to this expression. We know that the cosine term of this expression will evolve in time, taking values from minus 1 to plus 1. Therefore, one potential solution to our problem will be setting a equal to 0, which is a trivial solution that implies no motion. An alternative solution will imply that the term between the parentheses is equal to 0. Thus, minus omega squared times m plus k equal to 0. From this, we can find omega n, isolating it as the square root of k over m. This omega n, which emerges naturally from the solution of our ODE, is known as the natural circular frequency of the system and is usually measured in radians per second. It can be thought of as the angular velocity of an equivalent circular motion, such that one cycle of circular motion takes the same time as one vibration cycle. Coming back to our solution to the equation of motion, we have that the displacement of the system evolves in time as a cosine function with amplitude a and phase phi. We already defined the natural circular frequency of this motion as the square root of the stiffness over the mass, but we don't know the values for a and phi. These variables are to be found by making use of the initial conditions. Usually an initial condition of displacement, u at time 0 equal to u naught, and an initial condition in velocity, u dot at time 0 equal to v naught. Evaluating these two initial conditions will lead to a system of two equations with two unknowns, from where the following expressions for the amplitude A and phase phi can be obtained. Please note that these definitions of A and phi are expressed in terms of the initial displacement, the initial velocity, and the natural circular frequency of the system. Let's now look into formulation B, where our ansatz for the displacement u of t is expressed as the sum of a cosine function and a sine function. Differentiating two times with respect to time, we arrive to the following expression, and substituting the displacement and the acceleration into our ODE, we find this new expression. Again, we realize that the non-trivial solution to this problem will imply the term within the brackets being equal to 0. And therefore, these will lead to the definition of the natural circular frequency of the system, as also discussed before. Finally, having defined omegas of n in terms of k and m, the remaining unknowns are the amplitudes of the cosine and sine components, a1 and a2. As before, these amplitudes can be obtained with reference to the initial conditions of displacement and velocity, leading to a1 equal to u naught and a2 equal to v naught over omegas of n. In the case of formulation C, expressed in terms of complex exponentials, we postulate an ansatz for the displacement u equal to an exponential function elevated to lambda t, where lambda is a complex value. Differentiating the displacement twice to arrive to the acceleration gives us lambda squared times e to lambda t. And substituting into our equation of motion leads to this expression. We now realize that the left-hand side of this equation is the product of an exponential function, whose shape is well known to us, and the term inside the parentheses, which is m times lambda squared plus k. If we focus on this part of the equation and set it to 0, before isolating lambda squared will lead to minus k over m. That minus sign plays an important role, as we will see now, since solving for lambda will yield a plus and a minus I times omegas of n, where I is the imaginary number. Going back to our equation of motion, we have that the complete solution of the ODE will be composed by two complex exponential functions, one with a positive exponent and another one with a negative exponent. Finally, by means of Euler formulae, we will arrive to the following expression that is directly equivalent to the previously found solution for formulation B, in terms of cosine and sine functions. As before, we can make use of the initial conditions to find the value of the amplitude A1 and A2. In summary, we have solved the ODE defining the motion of an undamped single degree of freedom system by means of three equivalent formulations in terms of amplitude and phase, a sum of trigonometric functions, and complex exponentials. You will find that different academic texts will prefer one of these expressions over the others, depending on which part or features of the structural motion they wish to highlight. We should understand, however, that all the three solutions are equivalent, as they correspond to three alternative representations of the same harmonic motion. They will all describe a motion where the mass moves back and forth at a constant rate and amplitude without loss of energy. The temporal evolution of this harmonic motion will be defined by the initial displacement, with the displacement at time 0, and the initial velocity, which is the first derivative of displacement, or what is the same, the slope of the displacement history curve at time 0. An amplitude, which will depend on these initial conditions, a phase, which will also depend on the initial conditions on displacement and velocity, and a period of vibration, which is equal to 2p over the natural circular frequency of the system, omega sub n, that depends only on the stiffness k and the mass m of the translating single degree of freedom system, and it's therefore intrinsic to it.